You have seen this before. Hundreds of players trying to survive a deadly game. One wrong move and you are out. But what if I told you we could create this iconic scene using AI? In this video, I'll show you how to design the actual red light green light game of Squid Game using computer vision, pose estimation and real-time inference. So welcome to FreeBirds 2 and let's design ML-based surveillance system that can detect the movement violations for you. So first we have this raw problem statement given to us by the commander. In the red light green light game, players are allowed to move during the green light. During red light, any detectable body movement leads to elimination. The challenge is to build an AI system that can watch 100 plus players in real time and instantly detect if anyone moves during the red light phase. The system must be accurate, fast, and robust under varying conditions like occlusion, lighting, or player diversity. So, as per our ML system design framework, the that I already discussed in our previous videos, you can watch that first and link is in the I button or video description. So as our first step is problem formulation. So in this first step, you set your objective, that is classify whether a tracked person has moved significantly between the frames during red light, and real time movement detection based on the object detection, that is the finding people, then pose estimation tracking the body joints, then the motion analysis that can detect the movement from pose over the time deltas. Okay, then we have to define our task. Our task is simple. We have to do binary classification here to predict whether the person moved or not. Okay, and our input is a sequence of 2D pose key points for each player recent frames, and the output is a binary classifier, that is 1 or 0. And the features we need for this problem statement are like joint positions of each player, pose deltas that a player move from a last frame to this frame, and the velocity or acceleration of the limbs in that point frame as well. Okay, and the edge cases involved occlusion, jittery cameras, partial key points, or the false movements like wind, twitch, eyes twitching, like these kind of movements we should not consider as the violation. Okay, then ask about the data sources to your interviewer. His interviewer has the data sources, ask what kind of data they have and where the data is placed so that it can help in building the data pipelines for us. And then ask about your assumptions. In that case, I assume that the game has a static wide angle cameras are installed and stable. Players remain stationary during the red light and players are fully visible and upright during the most of the game. Environment conditions like lighting, wind and shadows are manageable. Okay, and to clear why we need ML for this problem statement. So because we need ML as a hybrid approach here, because the pose estimation, movement classification, player tracking can be done with a great accuracy with ML only. And for the rule-based approach, we can use thresholds for movement violation detections as well. Okay, after all this is done, ask and clarify interviewer about the functional and the non-functional requirements that helps you clear your scope much better. So I created these functional requirements that shows what the system must do, and what I have to do are detect human players in the camera frame first, and then estimate the 2D pose key points for each player, track each player uniquely across the video frames, detect the red light and green light phases. During the red light, detect the movement violations using the pose delta analysis, raise an alert or flag if the person moves during the red light, provide visual feedbacks like rounding boxes as well, and log all the events like player IDs, timestamp, movement and decisions as well, and support a configurable movement threshold and pose smoothing, and handle multiple players around the field as well. And similarly, for the non-functional requirements, that means how well it does in the real-time conditions. That's what I have to take care about is the real-time latency. It should be fast, and the accuracy that it should work on a 95% precision and recall for the movement detections as well. It is scalable to the 100 plus players in the multiple camera streams as well. It is robust, that it can handle the different lighting conditions, different camera angles and the wind conditions as well. It is fault tolerance and logs and retries on drop frame and tracking errors as well. It has the security and privacy. It doesn't store or leak the raw footage unnecessarily. It is transparent that it can log why it flags some player or why not with the threshold values as well. So when this is done and finalized with your interviewer, then talk about the matrices, offline and online matrices both, because offline matrices ensure your system catch violation without any falsely accusing innocents while maintaining the clean, stable key points for downstream logic. And the online matrices ensure that the system should stay fast, stable, and trustworthy while deployed, especially when stakes are too high, like in the Squid Game. So offline matrices that I think best are the precision, recall, key point stability score that measures the jitter across the frames when the player is stationary, and the tracking consistency as the percentage of the frame when the player ID is maintained correctly, and the frames drop rate as the percentage of frames skipped due to inference failure or the bottlenecks as well. These are the like basic offline matrices that we should take care and to maintain as well. We should skip the matrices like F1 score as it's a balance between the precision and the recall. It is critical in the edge cases like a subtle movement, but not as actionable as precision and recall individually. And we can also not use the pose estimation accuracy here, because as the key point wise accuracy of the pose model, it is not meaningful unless training your own pose model here at the first. Okay, and similarly for the online matrices, I think the best ones are the inference latency, as it's a real-time system. It takes 200 millisecond less time as the movement go undetected or feel laggy. And then we use the violation detection rate, that it is calculated as the movement violation detected versus the total red light events, that can help us to see that how many actual violations it can detect in the red light phase. Okay, so after you have the requirements, you have the matrices, you have the problem statement formulated very nicely, then you can move to the high level system design that I created here as a hybrid of ML and the rule based approach. So as you see in my design, how the flow goes from the video input to post detection to post tracking along with the feature extraction, then all feature goes to the hybrid model and decision phase, and the out we have is the red or the green signal. And for the model based approach, I have to do pose estimation, player tracking, and optionally we can use the movement classification or a binary ML model as well. And then for the rule based approach, I have to do the final movement violation decisions, use of the delta thresholds or the smoothing conditions, and apply a confidence score to say this person is violated or not. And this trade-off of the hybrid decision system ensures we have a high precision and recall. The system meets a very low latency requirement, and it remained explainable and trustworthy in the real world games. And here is the pro tip for you: start always simple and iterate. Always begin with the rule-based threshold to detect the movements as false positive or edge cases appear. Incrementally introduce the lightweight ML models like binary classification models, logic regressions, or the tree-based models to handle the ambiguity. Now the question occurs, why this approach is best? Why we use the hybrid approach? Let me clear this out as well. The first benefit of this approach is the problem is structured and the well constrained. Because we have the input that is clear and standardized, we have the output that is also cleared and standardized as well. Environmental conditions like static cameras, winds, upright players, they can be controlled as well. And the conclusions, we don't need a deep learning end-to-end model here. Instead, we can leverage the existing computer vision pipelines and make smart decisions on it. And the next benefit is pose estimation, that we use the MediaPipe framework by Google here, that helps in 2D joint estimation that converts the pixel to a structured XY points per player as well. And there is no need of training from scratch. It can work really better on the 50 to 100 players in the frame as well. And it is easy to pipe into the next stages like tracking and the decision logic as well. Pose estimation is a solved problem. That is pose estimation is a solved problem in more structured way. We don't need to reinvent this. And why I use MediaPipe over open pose here because MediaPipe for real-time production environments with 50 to 100 plus players are very good. But we can only use the open pose if I need a maximum accuracy. I have very powerful GPUs as well, and I can afford the latency as well. But here we don't afford the latency. We need a very fast system. We need a very fast system here. That's why we use the MediaPipe. And the third benefit is player tracking using the DeepSORT, because now the MediaPipe only helps us to detect the joints, but it can't identify each player uniquely. So that's where we need the DeepSORT. It helps in the maintain the consistent unique IDs across the frames. It handles dozens of players per frame efficiently. It can recover from the partial occlusions or the dropped detections as well. It works on the top of bounding boxes from the pose models as well. Okay, because we don't use a track by detection, because as I already said, the MediaPipe can lose player identities or uniqueness or swap them. That leads to false positive or negatives as well. But there is another tool that we can use that is called as fair mode. But here we don't use the fair mode because fair mode is more accurate on tracking benchmarks, but it is very heavier and it is very hard to plug into the existing pose detectors, and it is a overkill here. So that's why we use this smart approach to use the DeepSORT here. So for very start, we can use the logistic regression or the shallow MLP, because the ML classification is optional. It is only used to assist in the ambiguous cases. Okay, so we can start with the logistic regression to support or smooth the rule-based systems, not to replace it entirely. Okay, and then the final question, why rule-based for the final movement detection? Because movement is deterministic only during the grid light. So if any joint moving is greater than the threshold, we call it a violation. But how much movement is subjective? So that's where the ML helps before this rule is applied. So here is the summary of the ML based, rule based or the hybrid based approach that gives you a clear view why we use the hybrid approach, because it has everything better and balanced for us. Next, let's move to the data pipeline creation, our next step in the ML design framework. So as we have input from the RTSP IP cameras or the local webcam footages with a frame rate of 50 to 30 frames per second, and the resolution is 720 to 180p. Okay, and this problem statement that we are doing a red light green light game of Squid Game can have multiple cameras supported via a wide coverage as well. And for each frame, we do the frame processing. That is, we can resize the frame, we can normalize the pixels, we can convert the BGR to the RBG using the MediaPipe, or one optional thing that we can do is background subtraction or the stabilization as well if the camera moves. And then the next thing is feature extraction for the pose estimation. We can use the MediaPipe here that can use multiple models like Blaze Pose or the Pose Landmark to give us a 2D key points for each person, just like a ID or the key point of the nose, less twist, waist, all the like body points that it has. And for each key point, it include the XY pixels coordinated with the confidence score as well. And then we use the DeepSORT to create a unique identities of each of the player. For each input, we detect the pose and or the bounding box, and for each output, we got a unique player ID per frame across the time, and maintain the player's identity despite any kind of occlusion or jitter as well. And to detect the violation, we have these features about the pose history buffer, that for each frame, while the light is red, we have to maintain a sliding window of the n frames of key points per player. That means during the red light time only, because it enables detection over the time and filter out the jitter via smoothing or multiple other techniques that we can discuss further. Okay, so that's how you can like only build these kind of features while the light is red. Okay, and for the light red only, we can create features such as the pose deltas, joint velocities or accelerations, normalized motion features, because whenever a player moves from the last frame to this frame, we have to calculate the pose deltas as well. So if there is a pose delta, we has to calculate that feature, and we have to pass that feature to our ML model, and that ML model will decide that how much confidence it has that the player violation occurs or not. Okay, and then we have to pass all these features into our logistic regression model, and that will return whether a player moved or not with the help of 0 and 1. And for the role based approach, we can apply a hard threshold on movement matrices. For example, if any limb moved, that is by x pixels, consider a pose confidence and the consistency across the frame with the smooth joint signals, and the output is movement detected, true or false. Okay, so whenever a person just shifts his arm, leg, or any kind of body part, and that changes from the last frame, that considered as a violation. Okay, so all these features are created only in the red light phase only, because we can manual toggle our model to run via the control panel programmatic approach, because we need only flag violation during the red light. So as you can see, this is the data sample here with all the feature and the label along with the red light game phase as well. So here are the variable description as well for your help to know which kind of features are the best for the red light pose violation detection model as well. Now the part comes here as the model training. So now we have the data covers with us from the very traditional approach. Now you want to create a actual ML based model out of it. So here we are using a hybrid approach. We have the pose estimation, we have the tracking, we have the feature extraction, we have the ML model, and then a rule based approach to suppress the false positives. For our training set, train data for a 70% data, our 15% data is validation, and the 15% data is test. So to create our baseline ML model, our goal is if we give some features from the joint motions to predict whether a player violated the rules or not, it can use a simple logistic regression or the tree-based model as a baseline, and it can get all the numerical features from us and give us the binary output. And for the rule-based model, we have the rule that means violation is equal to any joint movement that is greater than some threshold for that can be called as a violation. And for this, pros are that it is transparent, it is fast, it is deterministic, but the cons are it is sensitive to jitters. So that's why we need ML model here. That ML model can work with the rule-based model to not give us the false positives examples here. And the question is how you choose a good test data, because for that we have to select the clips or the frame with different players, lightings, and occlusions that include a few of the true positives, a few of the true negatives as well, edge cases like minor jitters or the background movements as well. And that helps in test our hybrid approach very well. And now comes part of hyperparameter tuning, and for that we use stratified k-fold hyperparameter tuning to tune our logistic regression model. And now the question comes, why only these tools or models we use? Why not other tools? So let me clear that as well. We use the logistic regression here because it is very simple, interpretable, and it is fast to train and inference as well. It works really well on numeric data and very easy to optimize as well. On the other hand, the tree-based models are hard to interpret, risk of overfitting, need to fine-tune, and not good for real-time inferences. But we can use the tree-based model if our logistic regression is underfit, you have a large amount of data, and you want a better recall on the edge cases as well, and you are post-processing offline, not on the real time. Okay, then why we use the stratified k-fold here, not the other k-fold methods? Because the problem we have is binary classification with the class imbalance. In the most of the red light frames, players do not move. So if we use the regular k-fold, then the random split of data happens, and some folds might contain only zeros and mostly contain ones, lead to a unstable model training and biased performance estimates as well. But the stratified k-fold ensures that each fold has same class distribution as the full dataset, and it preserves the movement and the no movement ratio in every fold as well. So that's why I choose these over others for faster model and fulfill our non-functional requirements as well. So now Let's move to the online inference. So whenever a video input got fed to our pipeline, we perform data pre-processing and the verification using the following tools. We use a MediaPipe for real-time to-depose key points. We use the DeepSORT for player ID tracking. We use the OpenCV to frame grabbing and the video decoding and the image deprocessing. We use the NumPy and Pandas for the feature generation and processing. We use the Pydantic for the input and output schema validation. We use all this, and I already clarified that why these are the best in the previous slides as well. Got it? And then create some features using this and while training our model. And for deployment, we can use fast API that is very lightweight, asynchronous, and the Python native, and perfect for the wrapping model in the API. We can also use Flask that is okay but has slow and synchronous functions that can be only used for the demos. Another one is Django that is a too heavyweight and overkill for this serving predictions. So for the servers we can use UVCon, that is asynchronous server gateway inference server, for the fast API that is fast, scalable for our use case. Other one is Gunicon that is slower for asynchronous but better for Flask, and it is only used with Flask if needed. So at last we choose the best of us, that is fast API with the UVCon. That the fast API with the UVCon is the best solution for fast and scalable deployment tools. And for the deployment style, we can use Docker and the Kubernetes here, as Docker helps us in reproducible deployment strategies, and Kubernetes helps us in scaling to more cameras and the larger crowds as well. So at a production level, it works like this. The fast API app runs and predict endpoints, receives pose and the tracking data, calls the classifier, validate it with the rule-based logic, and return the JSON, that is violation, confidence, reason, and the frame ID or the player ID as well. And now the point comes for scaling and updating the pipeline or the model, that is more crucial in the system design part. The problem we have is, as the game size grows, so that the cameras grow, so that the players grow, so that the ML inference per second time is also grows. Because at a production level, our system should have many cameras, a real-time latency should be very, very less, and continuous movements and continuous improvements, fail-safe and monitoring as well. So for scaling increase in demand, we can use parallel pipelines, video level or the player level. The video level parallelism helps us to process multiple videos or cameras in parallel and scale horizontally across the cameras. A player level parallelism helps us ensure that within one video, we split the pose tracking or movement checking per player ID, granular CPU GPU parallelism as well. But at this level, video level parallelism here, because that helps us to get a viewpoint from all kind of the cameras as well. And when the size of the data and the model increases, we use the data parallelism here, because for data parallelism that is recommended for this kind of use case, we can split the data by players or the frames. We can run pose estimation or tracking per player or each batch of frames as well. We can send to multiple CPU cores. We can queue based streaming by using Kafka's and RabbitMQ as well. And why we use data parallelism here? Because each player movement decision is independent per frame, ideal for the real-time inference, and easy to batch and retry failed segments as well. And why not the model parallelism here? Because model parallelism actually works for larger models like LLMs or ResNets, and here we are using a very lightweight models like MediaPipe, DeepSORT, or a binary classifier as well. So there is no need for the model parallelism here. And for the A/B testing and deployment, we need it, as we try new movement logics at different thresholds or smoothing parameters. We measure the impact of false positive and the negatives as well. We compare the model 1 with the model 2 before the rollout as well. And for the model monitoring, we can use MLflow, as it has a versioning of models, deployment experiments, and it is tailored for the ML and great logging capability it has. And we can use Optuna, as it has hyperparameters tuning experiments, and it has very lightweight features. And other tools that might help us in that are for model health and drift detection, we can use Evidently AI. It create lightweight drift dashboards. And for live alerts, we can use Prometheus or Grafana that can help us in real-time metrics and alerting. And for the model failure logging, we can use Sentry, Loki that helps in log exceptions and the data snapshots. And for the inference time tracking, we can use Prometheus or StatsG that helps in catch the bottlenecks per model stage. So for our whole project, we use this architecture and all steps are done now. So for this, interviewer might ask you some more questions about your choices, and you should be ready why you use some tools or method, why not others, with all the trade-offs as well. So for your help, I create some interview questions that you might study and check based on the knowledge that we use to create our design as of now. The questions are like, how would you ensure that the violation detection pipeline consistently operates under the low latency with 100 plus players on screen and multiple cameras as well? Why did you choose MediaPipe over OpenPose or YOLO 8 Pose, and how would you switch if real-time constraint fail? Describe how you evaluate the tracking consistency of DeepSORT and what failure models you expect in crowded scenes. How would you mitigate them? Design architecture that can scale horizontally for 10 camera streams, each detecting up to 50 players in real time. What components need to be stateless here? And why is precision more important than recall in this system? And would your answer change if deployed in a real tournament? So all these questions helps you get a good grip of this project. So just be ready and read all these questions and answer that I already given here very carefully. And if you have any question, just ask in the comment section. Just be with me, and in our next video I will teach you how you can design the Spotify music recommendation system. So just be with me, and if you want to learn about generative AI, agentic AI, prompt engineering, or data science and machine learning, you can watch my videos on YouTube and also read my blogs on Medium. We'll meet in our next video. Thank you so much.